Greetings to all. I'm very happy to present part of the work belonging to my thesis project. This work is titled Structural, Electric and Magnetic Analysis of the Lead-Free Multiferroic Solid Solution, BCTC, doped with cobalt ferrite. This work was carried out in collaboration with Guillermo Manuel Herrera Perez, Jonathan Zamora Mendieta, and Armando Reyes Montero. Today, electroceramic materials are widely studied thanks to their possible and diverse application in the technological field. They are useful in devices such as magnetic field sensors, power generators, and magnetoelectric RAM memories. In this work, the multiferroic ceramics PCTC CFO with X equal to 0.1, 0.3, 0.5, 0.7, and 1 molar percent were synthesized by the mixed oxide method. The effect of cobalt ferrite on the electrical and magnetic behavior of the ceramics was studied. X-ray diffraction, scanning electron microscopy, and Raman spectroscopy analysis were also performed in order to characterize the structure and morphology of the ceramics. To carry out the synthesis of the ceramics, stoichiometric amounts of the precursor oxides and carbonates were weighted. Later, they were ground and mixed in an impact mill to later give them a heat treatment at 1200 Celsius, with a respective previous decarbonation process. In this way, ceramic powders were obtained, which were subject to a sintering process where they were ground with ethanol in a planetary mill. After drying the powders, pellets were made with an hydraulic press, and these were sintered at 1400 Celsius. The pellets obtained were carried out for structural, electrical, and magnetic analysis. Regarding the structural analysis, it was found that all the ceramics presented the characteristic diffraction peaks for a perovskite, in addition to peaks corresponding to secondary phases from possible residual carbonates. In the diffractograms, no peak corresponding to the espinel-like structure of cobalt ferrite was observed. These results give rise to a deeper analysis by red field refinement, with which it will be possible to note in greater detail the influence of cobalt ferrite in the crystallographic parameters and on the proportion of tetragonal, rhomboedrical, and cubic phases of the perovskite type structure of the BCTC. Regarding the Raman spectroscopy results, the spectrum was convoluted and fitted curve was obtained. A characteristic pattern of a mostly rhomboedral perovskite is observed. A Raman shift was noted at lower wave numbers for the EP04 vibration mode. This mode corresponds to the stretching of the bond of the titanium and the zirconium cations with the oxygens to which they are coordinated. The Raman results indicate that there are bond elongations that are favored with the increase of dopant in the ceramics. The scanning electron microscopy results show a gradual decrease in the density and particle size of the ceramics as the proportion of dopant increases. Again, this may be due to a microstructural stresses or structural deformation, closely related to the increase in dopant concentration. On the other hand, electrical and magnetic analysis were carried out on the samples. In the ferroelectric hysteresis cycles obtained at room temperature, a considerable decrease was observed in the values of maximum polarization and remanent polarization as the dopant concentration increased. These changes can be related to an increase in the proportion of the paraelectric cubic phase of the BCTC, which in turn leads to a decrease in the proportion of the rhomboedral ferroelectric phase. On the other hand, the decrease in grain size could also be closely related to these changes in the ferroelectric behavior of the materials. Conversely, as the concentration of cobalt ferrite in the ceramics increases, an increase in the saturation magnetization of the ceramics is observed, but the coercitive field is practically the same in each cycle of the figure 7. This change makes us notice the effect of the increase of the dopant in the ferromagnetic characteristics of the ceramics. When carrying out the dielectric analysis of the materials, the curve of figure 8 were obtained, where different behaviors are observed for each sintered ceramic. In general, the decrease in the dielectric transition temperature is notable. This indicates that the orthorhombic ferroelectric to cubic paraelectric phase change of the material occurs at lower temperatures as the proportion of dopant increases. In turn, higher amounts of dopants cause lower values in the maximum dielectric constant of the materials, and a phase transition with an increasingly diffuse behavior. In conclusion, dense multiferroic ceramics were obtained by the mixed oxide route. The XRD patterns and Raman spectra suggest a change in the perovskite-like structure of BCTC related to the radio of dopants in each sintered ceramic. The shift of the peaks corresponding to the vibrational mode ET04 suggests that doping with cobalt ferrite promotes an increase in the bond distance between titanium and zirconium cations with the oxygens to which they are coordinated. The density and grain size of the obtained ceramics decreases as a proportion of dopant increases. Ferroelectricity and ferromagnetism change inversely proportionally with the increasing amount of dopant. The ferroelectric phase transition temperature decreases with small increases of amount of ferromagnetic dopant. Finally, I want to thank all the collaborators of this work and the XDR lab at UNAM. Also, I want to say thanks to Nanotech Optical Spectroscopy and X-ray labs at CIMAP, and also to Papidunam Project EA 102622. And finally, I want to thank all the participants of the International Materials Research Congress of the year 2023 and all members of its organizing committee. Thank you to all.